Oh, and I know you can't see it, so we'll hop over there in just a moment. Um, okay, so there are no real announcements. Um, just the same. We're going to go ahead and do the second half of section 1.5. I am streaming a copy of this to YouTube, so we can always watch it there if needed. And then I'll be monitoring the chat. So if you have questions there, you can use the chat to get my attention. Let's hop over here. Let's show the chat like this. Okay. All right. Let's see. Yeah. So no real announcements. Put you here and grab you. And we set an alarm. Why does it keep defaulting to the waiting room? Okay. Anyway, let's do view. Single page. That's what we want. Why does it look weird? Okay. Oh, that's where we left off. Okay. So let's see. Oh, let's do this. Like this. Nope, not that one. This one. Okay. That's better. All right. So we were just kind of making our way through transformations of graphs. To me, the simplest way to just kind of walk through this one is just to kind of keep working through it. So we're about halfway through this presentation, so we're just going to kind of keep moving. All right. So let f of x be the absolute value of x, and then g of x is going to be 2 times absolute value of x, and h of x is 1/2 times the absolute value of x. Let me see. It's probably, as I see the chat. Okay, let me think about it. Yeah, let me let him in. Okay, so what I have to do. Oh, I forgot to switch this back. Okay. Let's click here. Let's go to users. And let's try to get them credit. I don't know who that is. So I'm gonna remove them. And okay, you can get in. Yeah, I don't know who that is. So okay, let's hop back over here. We can close this. We can show this. So we gotta click here, show this, and then we can hop over here. Okay. So again, let's try it again. I know. Yeah, this should be streaming to YouTube, right? Let me check one more time. Yeah, it should be streaming to YouTube. Let's see. Did I get a notification? Probably not, because I don't have that set the way I want it. Anyway, let's keep moving. What's this? This is the end of week 6. So week 8 again. Let's anticipate exam 2 over the second half of chapter 1. All right. So f of x is absolute value of x. Is this slowing down again? Ugh, we're probably ready to rock and roll. What time is it? Because I'm gonna lock the meeting at the 15-minute mark, because the reason it kind of takes a while is like every time I have to let someone in, it resets everything, and I have to like reset it all, the whole thing. Okay. So just remember that absolute value of x is the v, right? And then we're going to see what happens if we multiply the outside of our basic function by a number larger than 1, and if we multiply the outside of our basic function by a number between 0 and 1, right? So I think last time we were making tables, right? So we chose some values for x, and then found the corresponding f, g, and h, right? So notice that the absolute value of 2 is 2. 2 times 2 is 4, and half of 2 is 1, right? Absolute value of negative 1 is 1, times 2 is this, and then 1 times a half is this guy, right? And we just do that going across the board. We basically take these x values and plug it in each function, and then write down the output. So then what we do, we're going to just plot all of these ordered pairs. And let's see if we can make an observation on how these transformations or manipulations affect our graph. Okay. So the blue is the original function, which is absolute value of x. Okay. Notice if we multiply the outside of our basic function by a number larger than 1, we call that a vertical stretch. It got more tall and skinny. It got stretched in a vertical sense, right? So again, if we multiply the outside of our basic function by a number larger than 1, we get what's called a vertical stretch. If we multiply the outside by a number between 0 and 1, we get what's called a vertical compression. It gets shrunk horizontally. All right. Okay. So let's keep going. So then the graph of 2 times absolute value of x is going to be the basic graph is going to be vertically stretched by a factor of whatever that number is, 2 in this case. If we multiply the outside of our basic function by a number between 0 and 1, we're going to get what's called a vertical compression or a vertical shrink by multiplying basically each y coordinate by a half. So the x coordinates stay the same, but the y values in that case got cut in half. Whereas in the previous one, the x coordinates stayed the same, but then the y's were doubled. Okay. Let's see. So the graph of a times a function, where a is on the outside, is obtained from the graph of f of x by multiplying the y coordinate of each point by a and leaving the x coordinate unchanged, right? So if we multiply the outside of our basic function by a number larger than 1, we get what's called a vertical stretch. If we multiply the outside of our function by a number between 0 and 1, we get what's called a vertical compression, right? So if multiplying the outside of our basic function by these numbers are causing vertical changes, what do you think happens if we multiply the inside of our basic function? Instead of the changes being vertical, what do you think it's going to be? All right. So let's see. So we can have the result here. If we multiply the outside of our function by a number between 0 and 1, we get what's called a horizontal stretch. If we multiply the outside of our basic function by a number larger than 1, we get what's called a horizontal compression. So typically, multiply. Wait a minute. I think I said it wrong. Let me back up. I just realized what I said. Right. So if we multiply the inside of our basic function by a number between 0 and 1, we get what's called a horizontal stretch. If we multiply the inside of our basic function by a number larger than 1, we get what's called a horizontal compression, right? So multiplying or doing manipulations on the inside of our basic function, it tends to elicit the reverse of what our intuition might say, right? So like notice here, we multiplied the inside by a number between 0 and 1. You would expect that, oh, it would get smaller in the horizontal sense, but actually it gets stretched in the horizontal sense, right? All right, I'm assuming that's everybody that's gonna make it into class. I think I'll let it be for now. I'm trying to decide. I'm gonna just go ahead and lock the meeting. Okay. Okay. So using the graph of a function y equals f of x in a figure whose equation is not given, sketch each of the following graphs. We have f of 1/2 x, f of 2x, and f of negative 2x, right? So if this is f of x that we see in red, if we multiply the inside by a number between 0 and 1, we can anticipate a horizontal stretch, right? Sketch the graph. So 0, 0 is still there. When x is 1, horizontal stretch. F of 1/2. Oh, when x is a half, the answer should be 2, right? Let me think about it. Mm-hmm. Yeah. So this is gonna, like, if we were to choose some x values, I'm trying to think. How can we do that? Yeah. Well, the first one we're anticipating a horizontal stretch, right? The second one is going to be a horizontal shrink. It's going to shrink horizontally by a factor of 2. So it's almost like we're dividing each x by 2. And the first one, it's like we're multiplying each x by 2, right? The y value should stay the same. So 1 point should be 2 comma 3, right? When x is 2, the output should be 3. Half of 2 is 1, yeah. So again, it's kind of the reverse to do the inside functions. This is like basically each x is being doubled, each x is being cut in half, each x is being cut in half and multiplied. Now this one has 2 transformations, right? It's shrunk horizontally by a factor of 2, and it's reflected across the y-axis. All right, so let's see. So again, the first one, oh, did I ever switch that over? Yeah. The first one, we're anticipating a horizontal stretch, right? So let's see it here. Stretch the graph of this horizontally by a factor of 2, right? Each point, this transforms to 2x comma y, right? So we did stretch it horizontally. And it's almost like you had to say x divided by that thing for it to behave properly to get a better sense of it. There are a couple of different techniques or routes to comprehend this. You have to just kind of discover one and choose what works best for you. For me, I know that the reverse is what's going on there, right? And there also seems to be this notion of x divided by that thing in order for it to behave properly, right here. If you say x divided by a half, it's going to be the same as 2x. But that's only on the insides where it's a little bit backwards. So then the second one, we said a horizontal shrink by a factor of a half. Again, if you divide by 2, you get a half. Okay. So then we multiplied the inside by a negative, so it flipped horizontally across the y-axis. And then we still did the horizontal compression by a factor of a half. So sketch the graph of this function. Notice that the highest exponent is a 2, so we can anticipate a parabola. We have the coordinates of the vertex. Our h, let's do it this way. Our h comma k, in this case, would be 1 comma 3. The leading coefficient is actually negative, and it's going to be here. Let me see. Oh no. Man, I don't know why. When I get here, I just like I all of a sudden get like super sleepy, and I just want to go to sleep. So we have the vertex, which is going. It should be 1 comma 3 here. Notice that this is actually our leading coefficient. The 3, we should probably move it over on this end. But since the leading coefficient is negative, it should open downward. And then that plus 3 tells us to move up by 3. All right, so let's put all that together. I'm just going to do a rough sketch, x and y. So we said the vertex occurs at 1, 3, so that's about here. All right, if that was like a 1 and a 3, I'm going to say 1, and this is our 3. Okay. We said it opens downward, and then oh wait, we've already factored in that 3. We don't need to factor in that 3 twice, right? So when we go right 1 and up 3, we're good to go there. And then it was let's see, the 2's on the outside, so that's a vertical stretch by a factor of 2. So then we have this axis of symmetry, right? So when x is 1, I think the answer should be 3, and we're okay. Let's do when x is 0. When x is 0, this is ultimately going to be 1. That's a 2. 3 minus 2 is 1, right? So I got it. 3 minus 2 is 1. So when x is 0, y should be 1. But if we go to the left one, we're at 1. If we go to the right one, we should also be at 1, right? Because we're using the axis of symmetry. And I'm just going to let that be enough. Okay. So the basic functions of parabola, we move it right by 1, right? I think we accounted for that. It says stretch vertically by a factor of 2. Reflect vertically because the negative is outside our basic function, and then move it up by 3, and I think we got something similar. All right. Okay. So for an artery with a radius r and a velocity v of the blood flow at a distance from r from the center of the artery is given by this. Okay, where c is a constant that's determined for a particular artery. We write v, which is v of r, or v of r, which is c times r squared minus r squared. Starting with the graph of y equals r squared, sketch the graph of vr given that it already has a radius of 3. Okay. So let's see. Do we know what c? C is a constant that is determined for a particular artery. Starting with the graph of y equals r squared, sketch the graph of y equals vr, given that the artery has a radius of 3. Let me see what it says. Okay, v of r is this. Where does c? Where's c come from? Oh, here it is. So c comes from here. Wait, you can't see that. Oh, maybe you can. So c was given here. It says the radius of the artery is here. What's the little r? Center of the radius of the artery. Okay. Let me see a little r. So we got big R, we got C, y equals little r. Did we just let the little r persist? Okay, I think we let the little r persist. Let me see one more time. Sketch the graph. So we plug in the 3 and the 10. That is difference of squares. We can distribute the 10. We get something like this. Where's the negative? I see that one. Oh, is that the final thing right here? So notice that this 9 times 10 to the 4, that's just a number. So then this says what? We can stretch it. It's on the outside. We can stretch it vertically. Let me see. By a factor of that. Then this negative is on the outside, so flip vertically over the x-axis. And then this says move it up by, what is that? 90,000? And you see it there, right? The velocity of blood flow decreases from the center of the artery to the artery wall, where R is 3, where it ceases to flow. The portion of the graph corresponding to the negative values of R do not have any physical significance. Okay, so we're gonna let that be the end. Let me see, what's the time? Oh, here it is. 2:25 until I think it's 3:15. So for the remainder of class today, what we can do is work the problem sets from Pearson. I'm just going to be available. Feel free to unmute yourself if you have questions, right? So we're just going to kind of work on our homework. Let me do, you can unmute yourself. So again, what we use for the rest of the class, use that time to kind of work on our homework. And let me share these notes with you. Okay. So I loaded a copy of the notes, anything that you saw me write. And then, so for the rest of the class, I'm just available for questions, right? I'm just available for questions. Hey, Google, turn the fan on. Um, oh, okay. Let's do, that will change things. Let me think about how I'm gonna do it. For me, can you hear me? Can you still hear me? Try to do your audio now.
What?
Yeah. Um, like pull up the homework and give it a go. Like let's choose some homework questions and try to work through those. And I'll pull it up on my end. So yeah, transformations. I want to say like essentially they're simple, but it's kind of like information overload. There's a lot of information in a little bit amount of time. So the only way I really know to kind of get it is just to kind of keep working it, and eventually it sinks in. There are like about 8 different categories or techniques, but in a general sense, outside manipulations cause a vertical change. Inside manipulations cause a horizontal change. Outside typically goes along with our natural intuition. Inside manipulations tend to be the reverse of our intuition. Um, and you just have to do the best you can. Again, connect with the tutors, and maybe like read up on how Pearson does it. So Pearson explains how to do every question, right? So that's why we use Pearson. They explain how to do every question. There's like an explanation. There's either video tutorials. There's also the ebook. The view and example to me, between view and example and ask my professor, ask my instructor, those are the most powerful tools of Pearson, in my opinion. Like between those two sources alone, you can figure out all of these. So I'm just trying to open up my Pearson and let's take a look at it. Again, I'm just here. Feel free to unmute yourself or use the chat. And as you kind of make your way through the assignment, make use of the Ask My Instructor. Um, make use of the Ask My Instructor, and I can pull it up and we can talk about it if I can log in. For some reason, it's like not logging in. So